matter in a variety of mechanical engineering disciplines, represented by ASME's technical divisions and technology groups. Before we get started, I will mention that we will have time for Q&A after today's talk. If you have a question, please type it into the chat or actually type it into the Q&A icon on your Zoom screen. It will be at the bottom. We will do our best to answer as many questions as possible. So as the presentation goes on, you don't have to wait. Go ahead and type those questions. Now, it is my pleasure to introduce Arun Veermani from the chair of the Safety Engineering and Risk Analysis Division, also known as CIRAD, and a scientist at the Pacific Northwest National Laboratory. Arun, I'll hand it over to you to kick things off and introduce our speakers.
Thank you, April, and hello, everyone. This Tech Talk is brought to you by the ASME Safety Engineering and Risk Analysis Division. We call it CIRAD for short. So CIRAD's function is to stimulate interest in safety, risk, reliability, and resilience as applied to the process of mechanical engineering. CIRAD hosts technical tracks at the IMECE conference, that is IMECE. IMECE conference organizes a Student Safety Innovation Challenge, coordinates closely with the Journal of Risk and Uncertainty in Engineering Systems, bestows the IU Vehicle Risk Analysis Award, and oversees the Risk Technology Committee. And now, let me introduce our speaker, Dr. Andrei Morozov. Dr. Morozov is a junior professor at the University of Stuttgart, Germany, and the vice chair of CIRAD. He completed his PhD at the Institute of Automation, Dresden University of Technology in 2012. In 2014, Dr. Morozov founded a research team at IFA focusing on the model-based analysis of safety-critical mechatronic and cyber-physical systems. Dr. Morozov has published 60 scientific papers and given more than 20 scientific talks, including presentations at ESA, DLR, BOST, MathWorks, Sanford Research Institute, and the University of California at Los Angeles. Since April 2020, Dr. Morozov has held the tenure-track professor position for networked automation systems at the Institute for Automation Technology and Software Systems at the University of Stuttgart. His team works on several projects in the area of risk, reliability, and safety of technical systems. And without further ado, Dr. Morozov, I'll hand it over to you to begin.
Thank you so much, Arun. Let me share my screen. Could you please confirm that you see my slides?
Yes, Andre.
Thank you so much, Aaron. Thank you, Aaron. Thank you, April, for the introduction and for having me here. And today we will talk about AI-based, artificial intelligence-based anomaly detection for technical systems. The presentation will consist of 4 parts. First, I will talk about some examples of safety critical systems, about system states, faults, errors, and also potential failures. After that, I'll go through the topic of anomalies, explaining what is an anomaly and what kind of anomaly detection methods exist. In the part 3, I will talk about our research results and in particular about a special deep learning based anomaly detector that we called Kraken. Actually, therefore, we have this guy in the first slide. And finally, I will finish with the challenges and solutions that we are currently facing in the area of deep learning based anomaly detection. So part 1, faults, errors, failures. In this slide, you could see sketches of 3 safety critical technical systems. It's a medical exoskeleton, flexible production line, and some kind of a smart city inhabited with intelligent transportation units, such as delivery bots, UAVs, and autonomous vehicles. So all these systems are complex in terms of they consist of different components, and all of them are safety critical. We don't want to have an injury for our patient. We don't want to have injuries for our workers, and autonomous driving is also a safety critical area. So another similarity between this system is that all of them consist of heterogeneous components, such as physical parts, different kinds of motors, joints, frames, hardware, computing hardware, network hardware, sensors, and of course, software. And the software plays actually a critical role. So, and such kind of systems are complex from structural point of view, as well as from the behavioral point of view. Many components, and these components interact with each other, resulting in many execution scenarios that could not be actually predicted and analyzed completely. So complex algorithms and distributed agents, the systems also are reconfigurable and repurposable. And of course, it could be artificial intelligence on board that makes the life even more complex in terms of the risk. Okay, so however, we could abstract such kind of system into a number of components, such as sensors, network parts, controllers, and actuators. So, and the lines between the components, they basically define the data flows. This sensor provides some information over the network to this subsystem, to this controller, and so on. So, and each kind of component might have several kinds of faults. For example, if we are talking about the sensors, we could have bias, drift, freeze, or sometimes it's also called stacked, or noise in the sensor data. So if we are talking about the computing hardware, we might have a bit flips either in cache or in memory. And the bit flip is a silent data corruption because of, for example, lowering voltage or electromagnetic induction, 0 change to 1 and vice versa. And such kind of faults can appear in the computing units. And if we talk about the network, we might talk about timing faults such as delays or varying delays that also called jitter, or for example, package loss. And these are examples of internal faults. And beside that, we might have external faults. For example, if we talk about the autonomous driving, we might have bad weather conditions, or we might, such as rain, fog, and so on, or we might even have some problems with our camera, for example, blur or out of focus. And of course, last but not least, it might be some kind of hacker attacks. And these are, let's say, bad things that could happen with our system. So, and here in this slide, I want to explain that if we take the data from the and if we sum up the data from the sensor, the controllers, and network, they will form a kind of the pattern. And in each time of system operation, this combination of this data define the system state. Of course, it is continuous, but here I would like to simplify it, say that, okay, our system is jumping from one state to another. And this state, which I'm showing here, these are nominal system operation state. It means how we expect it to work, right? However, because of the faults that I talked about, the system could change the state from the nominal to erroneous state. A fault, we define it as a defect in the system, and the fault activation result in error in the system. So, and error is usually defined as incorrect internal system state. I mean, the system is still operating, it's still functioning. However, something is wrong inside, right? So, and the error tends to propagate because of one error. For example, if you have error in this sensor data, it could be transmitted here to this component, and the controller will send the wrong signal because of this sensor data. And this is called error propagation. And let's say the worst thing that because of the errors can cause failures. So, and failure is an incorrect delivered service when the system basically stop working or stop providing the service that it should provide, or externally visible deviation from system specification. So because of that, system could stop or it could continue operating, but in a wrong way. So, and the goal of the basically of the anomaly detection and error detection methods is to prevent the system failures, to stop the thing here. So we need to detect an error. We need to detect that we are in erroneous state. And we either need to mitigate or to recover from this error. So, and in order to do that, we could use anomaly detection techniques. Okay, now let's jump to the second part and let's talk about the anomalies. What are anomalies? What is an anomaly? Anomaly, there are many definitions and I summarize them into these two bullets. An anomaly is an observation or a sequence of observations which deviates remarkably from the general distribution of data. So this is the first thing. And second thing, the set of anomalies form a very small part of the data set. If we have too many anomalies, there are no anomalies anymore, right? So, and if we take a look into this, and if our system is defined with the vectors of this, of the speeds of this car, we could recognize that, okay, all the vectors show either to the left or to the right, and this vector has, you know, some angle here. So, and it deviates, and it is an example of an anomaly. So, and basically such kind of anomalies are the signs that we are somewhere on this zone. So we detect anomalies in the data. And if we work with these technical systems, in most cases, we are working with time series data. Time series is a series of data points indexed in time, right? So there are more general definition, temporal data. It includes time series, but also other kinds of data, such as, for example, images that have timestamps. So other two definitions that we will need to use is univariate data and multivariate data. Univariate data takes only one dimension. For example, this is a univariate data because this is the data from a single sensor. So, and multivariate data contains multiple dimensions. For example, if we consider the outputs of several sensors, or if we consider the images, these are multivariate data. So, and finally, the data could be either labeled or not labeled. And in our case, we are interested in labeled data sets with anomalies. So, and the labeled data set contains annotation for each element that determines this element is normal or abnormal. For example, here we could see an example of time series because we have 3 data, it is multivariate, and it is labeled because we have these red boxes around showing that, okay, here we have some noise, here we have some stockade, and here we have some offset. So anomalies could be roughly classified into 3 types: point anomalies, collective anomalies, and contextual anomalies. The easiest one are point anomalies, and they are quite easy to detect. So basically, you could see that some data is an outlier, so it deviates from the rest of the data just by itself. So more complex situation is a collective anomaly. For example, here we have 2 sensors, and you see the values of these sensors jump from low to high. So let's say it's okay to be here, right? So this one point is okay, but to having several points in a sequence, this is a collective anomaly. All together or forming some pattern, this makes an anomaly. And finally, we have the contextual anomaly. Like the easiest example is, for example, if we see someone wearing a mask and it is, for example, 2018 or 19, it is an anomaly. But if we see it in 2020, 2021, it's not an anomaly, right? So it depends on the context. And for example, here on this example, you see the sensor 2 have this oscillation usually when the sensor 1 is on the high value. And for example, here there are some oscillation when it is still on the lower value. And this is an example of the contextual anomaly. This is important because different methods need to be used to detect these 3 types of anomalies. So there are many methods for the anomaly detection. So it's a very big field, and lots of many researchers worked on that field. There are many classifications. I bring this one because we like them. We like this classification. So, and anomaly detection methods could be classified into expert knowledge-based method, model-based methods, and data-driven methods. Expert knowledge-based methods, they are used in the industry in most cases. For example, we could define, some range and saying that, okay, the value should not go out of this range. Or we could define some monotonicity check, or some trend. Or we could define some rules. For example, if we have a positive acceleration, our speed should grow, right? So if not, then probably we have some anomaly. Second group is model-based methods. Basically, the idea that we have a plant, we have our system, and in parallel, we run a model of the system or an observer of the system. And then we compare the outputs of the real system and the model. And if they not agree, if there is discrepancies in these outputs and discrepancies are rather big, then we are saying that something is wrong. And finally, we come to the data-driven anomalies, where we try to find anomalies based on the data that we get from the system. So, and here again, we have three groups of methods: statistical methods, machine learning, and deep learning methods. So statistical methods are used for a long time and used a lot. One of the example is ARIMA. It's basically a predictor that learns some patterns from the data and starts predicting the data. And then we compare the predicted value and the real value. And if this prediction is bigger than some residual, we raise a red flag. Machine learning methods consist of other methods such as k-means, dbScan, isolation forest. Most of them are based on some kind of clustering algorithms, for example. We identify the clusters of data, and if some data are out of these clusters, these are outliers. So, and finally, we come up to the topic of this presentation is a deep learning-based methods. So for the deep learning-based anomaly detection methods, they are based on deep neural networks. So there are different kinds of neural networks, such as multi-layer perceptron, recurrent neural networks, convolutional neural networks, and so on. And they, most of them, or at least these 6, they could be used for the anomaly detection. So, and here we have some examples. This is a multi-layer perceptron. This is a CNN, convolutional neural network. This is encoder-decoder, and this is LSTM. And about LSTM, we will talk a little bit later. So, and there are also 3 approaches how we could use this kind of deep learning methods to detect anomalies. Approach number 1 is classification. This is a supervised learning. Basically, we receive the data and we classify this data. Is it okay or it is an error? So, as I said, it is a supervised learning. Therefore, we need sufficient amount of labeled instances, both for good data and for the anomalous data. And this is actually the biggest problem of these classification methods. They show very good performance, but if we are talking about the anomalies, usually it is extremely hard to find a data set that has enough erroneous instances. Therefore, if it is possible to use such kind of methods are used if we have such kind of data. If not, then we jump to the approach 2 or approach number 3. The approach number 2 is prediction. We are using an deep neural network, for example, a recurrent neural network, as a predictor. It reads some history of the data and tries to predict the next state of our system. And then we compare the predicted state of the system with our current state of the system. And if they are different, then we are saying that something is wrong. So this method is good because it is unsupervised. We don't need labeled data. We just need enough data about the system, and then we could train our predictors. And I would say that I don't want to make a bold statement, but from my gut feeling, 70–80% of the deep learning based anomaly detectors, they are based on the prediction approaches. And the final approach is reconstruction, the idea that we encode the input data and then we decode, and then we assumed that after the decoding, this data would be similar. And if there is an anomaly in the data, they will not be similar. So, okay. So far, so good. And currently, it's a kind of, boom of the deep learning based anomaly detection methods. I mean, artificial intelligence is everywhere. And of course, lots of researchers are using and in most cases, just taking new architectures and trying to apply it for the anomaly detection. However, not all researchers are so positive about that. And you could see 5 recent papers, 2 of them basically saying that deep learning methods should not be used. And we could do everything with machine learning methods and with the statistical methods. Some other papers saying that, okay, we could use them, but not for every system. So, and in this slide, I would like to express like our point of view and our motivation to that. Let's take a look on this plot. If we have a simple system that doesn't have a lot of data, it consists of several components and these components are well known. So we don't have a lot of data. In this case, we should use expert knowledge and everything would be fine. And if the complexity of the system and the available data that we have to process increases, then we have to jump first to statistical methods, then to machine learning. And at some point, deep learning methods start outperforming the other methods. Of course, you might not agree with me, but this is a kind of the trend that is more or less visible in the presentations. So, and another thing is that using the expert knowledge, we usually can catch known anomalies that we know that such kind of anomalies can be, and we design the method just to catch this one. With machine learning and statistical methods, we could catch known unknowns. Like we know that such kind of anomalies could happen, but we don't know exact parameters. And the deep learning has a capability to detect unknown unknowns. So we could catch anomalies that we have not even thought about. Okay, let's jump to the third part. So, and here I will talk about Kraken. And Kraken is a deep learning based autonomous error detector. Basically, this kind of octopus that is connected to our system, reads the data from the controller, sensor, network. We call the thing access points. So, and inside it has a deep learning neural network, you can see it. So, and it basically distinguish, are we here or we here? And if we here, it raises the red flag. So, and also we played with hardware. And for example, here, my colleague Shong, in his hand, it is NVIDIA Xavier, special purpose embedded board. And we install this guy here and we connect to some robotic system. And if we detect anomaly, this slide goes to red. So here you could see that inside the head of this monster, we have a multi-layer perceptron. But as I said, multi-layer perceptrons are only one option to do the anomaly detection. And actually, they are not very good for the time series, because basically, okay, they are good classifiers, but for the time series, okay, we could use them and some sliding window, but they forget what was before in the time series. And in order to learn the temporal dynamics of the system, it is advised to use RNNs, recurrent neural network, and especially so-called long short-term memory. This is a special architecture. It is shown here. And this is a state-of-the-art architecture for processing time series data. So sometimes before also transformers were start using, but LSTM if we are using the prediction-based methods for the anomaly detection, in most cases, we are using LSTM architecture. It is very good to predict the time series data. So, and basically here is the workflow. First, we train our system using the available data, and then we put it into the field, into the operation, where it receives the data from the system for some time. Then after some time, it starts predicting, and then we compare the prediction with the current system state. And if we have the deviation, we say that it is an anomaly. Also, we are using the testing data, which is labeled, to evaluate how good is our anomaly detectors using precision and recall evaluation metrics. So in this example, we used an LSTM architecture. It is stacked LSTM. It consists of two LSTMs, one on top of each other. It looks back for 50 steps. Basically, it remembers last 50 steps, and it predicts one step ahead. So, and we train it with these training parameters. After that, using this model, we are doing the prediction. So you see, first we're learning for 50 steps, then we start the prediction. And for example, here we have a spike in our sensor data. And the prediction, this is a zoomed version of this part. The prediction is that we should be here, but the real value is here. We have the deviation. And because of this deviation, we are saying that we detect an anomaly in our data. So, and we are doing it using two methods. There are actually more methods, but you could do it either with fixed thresholds using the Gaussian distribution, or we can do it using the dynamic thresholds. So, but both of the methods are, let's say, okay. So, and finally, when we run this system, it could successfully detect, for example, sensor spikes, sensor noise, some offsets, network delay, and some bit flips. So, and also we evaluate the precision, how good is our detection using the precision and recall metrics. I will not go in detail, but basically this tells us the ratio of true positives to all of them or true positives to false positives. So we applied such kind of Kraken to several systems, to robotic manipulators, to medical exoskeleton that we have in our lab, to simulator of autonomous vehicles, and also to the model of a UAV. So we used not only LSTM, but also we used other methods such as even multi-layer perceptron, but also autoencoders and the methods not only from the deep learning, but also from machine learning, such as random forest or gradient boosting. So, and published some papers. And usually the results are the following. Okay, we have some data. For example, we have an accelerometer and we do fault injections, and this is the accuracy, and the best architecture is a hybrid CNN LSTM, or for example, here it is a gyroscope. And we also compared several architectures, and the best was the random forest. So let's say so far so good. And frankly speaking, 90% of the published papers about the anomaly detectors, they are like that. Okay, we have some system, we have some data, we trained some anomaly detector, we got it, we have something. But how to compare, how to automate this process? So our first step was the development of time series anomaly detection platform. So it is a software for MATLAB Simulink, where you could upload the data from your system, either univariate or multivariate. Then there are a number of predefined deep learning neural network architectures, such as LSTMs, transformers, and not only deep learning, we also have machine learning here as well. So, and there are parameters. So the parameters could be customized. For example, LSTM could be parameterized with the number of LSTM cells, the number of LSTM layers, loopback, batch size, and such kind of things. And each of these models, they have the parameters. So in the search space is actually very big. So we have some predefined parameters, but they could be customizable. So we have several detection approaches, such as prediction and classification, or auto-encoding. And then we could evaluate how good is our anomaly detector by fault injection. So this tool also, it is based on another tool that allows the injection of different fault types: offset, noise, stacked, and also multiple injection methods, where we could define duration and magnitude of the fault. So the tool is open source, so you could take a look here. So, however, I mean, still, even with this tool, or there are also other tools, but this is a tool, it is for MATLAB Simulink, so it's good that it is a model-based. Most of the other tools, they are in Python. So, but with such kind of tools, we still need a human expertise to design an anomaly detector. So, and this is basically the part where the real science could engage. So, and here are a number of challenges. So I have 7 minutes. I will go through them, explaining what are the next steps that have to be done on the area of the deep learning-based anomaly detection. So, okay, and the first challenge is basically how we automate the process, how we select the suitable anomaly detector. So we have the data from our system, we know potential faults and so on, how to select it. So the idea, basically, we need to use smart search algorithms that search between the search for optimal detection approach, deep learning architecture, and hyperparameters, basically what to put into the head of our Kraken. So, and also we could even do the combination or assembly of these anomaly detectors. So because depending on the faults that we expect in the data, for example, one anomaly detectors are good for the spikes, another good for drifts, right? So, and the third one is good for freeze. Also, the performance of anomaly detector is also very much depends on the parameters of the data itself. And we also could extract some features from the data. It could be simple features, minimum, maximum, mean, number of peaks, or it could be complex features such as cyclicity, volatility, subtrends. And by taking into account these features and expected faults, we could select a suitable anomaly detectors that we need, and even combine them if, for example, we expect several kinds of faults in this access point. So, and basically the next step, last but not least, we could do the dynamic switching of the detector, because, you know, the context could be changed. For example, if we are driving, like our system could change the state, and the data and the types of the faults could be changed. And in this case, we need dynamically to switch these error detectors depending on the context. So, and what we are currently working on is the following idea. So we have a system, we do the simulation of the system with or without fault injections. And basically we create a zoo of different kinds of deep learning based anomaly detectors. And we know that this one is good for this kind of data and this kind of faults, and another one is good for another kind of data and another kind of faults. And then when we are in the field, also using this information, we train the classifier that is able to choose between them. And when we are on the field, we analyze the data, incoming data, and also we analyze the system itself. So we analyze, for example, that, okay, the information from this sensor could propagate to this actuator and to this actuator. And if we have access point here and access point here, here we could expect the faults from these sensors, right? And taking this information into account, we can select a suitable anomaly detector. So this is the first challenge, how to select the anomaly detector. So the second challenge is how to select the access points, where to connect the legs of our Kraken. And this we are solving by the application of formal methods and simulations for error propagation analysis. So we analyze where the errors propagate, and we also need to change these legs dynamically depending on the attention. For example, if we are analyzing if we are trying to find anomalies in an electric car and it stayed in a garage charging, then we need to connect everything to the charger controller, right? But if we are, for example, driving on the highway, we need to observe speed, acceleration, and maybe some commands from the steering wheel. So the third challenge is how to get enough training and testing data. As I said, the supervised methods, they are good, but they need enough training data, and the training data should be realistic. And therefore, we're also developing the tools that allow us to do the fault injection. We could inject different kinds of faults, specifying fault event and fault effect. And also we're experimenting with augmented fault injection. Basically, we take a normal data from the system, and then we have a library of samples of different faults from other systems. And then we are using some GAN generative adversarial networks. Like you probably remember, GANs were used for creation of the deepfakes. So, and this is preliminary, the same idea. We are generating realistic faults. So, and even more, we are using reinforcement learning to, how to explain it? So basically we have our system and we could inject different kinds of faults to our system. And this is our environment. And we also have an agent that decides where to inject the fault and what kind of fault have to be injected. And we run this loop in the reinforcement learning fashion to identify what kind of faults, when and where will trigger the biggest errors in the system. So, and by doing that, we might have, for example, like a bad guy, one agent who is trying to inject the faults in the system, and the good guy as anomaly detector who is trying to detect these faults. And we put them together in the loop and they start learning from each other. So, and this is my last slide. So this is, instead of the conclusion, I would like to show this slide. So we are working on the anomaly detection on 3 levels. So we define component level, system level, and system of systems level. Anomaly detections on the component levels, here we are solving the problems, what kind of anomaly detector, what kind of the DNN architecture to use, how to select them, how to combine them, how to tune them, how to dynamically switch them based on the data that we are receiving. And here there are anomaly detectors for univariate time series data. When we go to the level above, to the system level, for example, a car, so here we start mixing the data science with system analysis. We identify the error propagation through the system, and we are thinking about the dynamic switching of the access points, where to take the data. And we are talking here about the multivariate time series data. And finally, when we go to the system of systems level, where we have the physically distributed systems, here we are really need to think about the attention switching and scaling of the methods, and also distribution of the anomaly detection methods over the hardware. I mean, it could be local edge devices in the cars that do system level anomaly detection. It could be a system of system level anomaly detection somewhere in the cloud, and also some pre-processing in between in the fog. So as a conclusion, I want to say that deep learning-based anomaly detection is very hot field at the moment. There are lots of research there. However, most of the research is basically we have a data, we train an anomaly detector and it works. There are these challenges that have to be solved in order to make it, usable. So, and we should not start using deep learning only by itself. It needs to be combined with the classical methods, with a system analysis method, with an expert knowledge, and with other methods for the anomaly detection. That's all from my side. Thank you so much, and your questions are welcome.
April, over to you.
Thank you all. Before we wrap up, I'd like to mention that if you're interested in obtaining a PDH certificate, look for a follow-up email. If you've opted into receiving communications from ASME, you'll see it soon. If you have a colleague who was unable to join us today, it will be posted within the ASME members page for the Tech Talk series, typically about 1 to 3 business days. If you'd like to request a Tech Talk topic or provide some feedback, a survey will appear in your browser window once this Tech Talk has concluded. The next talk will be presented by the Dynamic Systems and Controls Division on Friday, August 26th at 12 p.m. Eastern Time. Additionally, if you are an ASME member and would like to join a division, visit asme.org and log into your account. Click on additional info, and there you'll be able to select 5 areas of interest by clicking edit next to the technical division interests. By doing so, you become a member of those entities. Thanks again, everyone, for joining us today. We hope to see you again soon.